Hello everyone, my name is Kishore Gupta. I will present our paper Applicability Issues of Evasion-Based Adversarial Attacks and Mitigation Techniques. My co-authors are Dr. Dipangar Gupta and Dr. Jahid Akhtar. Let's say what is an adversarial attack. Here we will recognize this snow image as a dog by machine learning, but to a human it will be still as a dog. We can see that in this hill area there is some resemblance of dog, but it's still for any human they will recognize it as a snow. But a machine learning platform it is detecting it as a dog. As by definition from NIST, adversarial attack is manipulation of training data or machine learning architecture or manipulated testing data in a way that will result in wrong output from ML. From this definition, we can have three types of adversarial attack: poisoning attack, manipulated training data; evasion attack, manipulating input data; and Trojan AI, manipulate AI architecture. Example changes the weight values of any CNN. Let's see some example of adversarial attack. First example, some added noise kind of a sticker making a stop sign as a green light could be very harmful for autonomous vehicle. Second image, the biometric is getting fooled by wearing a glass. And third image, for medical science, a benign tumor was detecting as a malignant by some adding some noise which are completely unrecognizable by human. Let's see some types of adversarial attack like one pixel attack. Changing the one pixel, it changes the attack classifier. Second is the patch attack. Adding some sticker, it will change the classifier. There are other types of attack like FGSM, BIM attack, silencing map attack, JSMA, advanced CW. Here, basic and advanced are distinguished between the noise level they added. In basic attack, uh, many noise are added, and in advanced attack, very simple noises are added. There is also some other attack types like decision attack, hop skip jump, and default attack. Here an example of a FGSM attack type has been presented. A noise has been added to change the class of this goldfish to starfish. We can see that it becoming a starfish. Here the attack was created by added a sign and the class level get changed. We can see how a targeted boundary attack generates an adversarial example only by keep adding noise and sample from some predefined noise to a benign example until the images look like another image from a different class, while it still be classified as the true class of the original image. This is an example of Trojan AI where extra layer has been added which creates the misclassification. Different strategies of adversarial attacks are like retrain, which the adversarial example or retrained into the model, but limitation is it actually reduces the accuracy of the learning model. Another is input reconstruction of or transformation via using some PCA, low pass filtering, KPJ compression, and other proportional technique used to distinguish between that. But it's vulnerable to adaptive attack because attacker know what type of defense is used and it created a sample which can bypass those defense. Then there is a model modification where the machine learning model layer architecture has been changed to avoid this type of attack. If we go through all those attacks, we can see that adversarial attacks has a significant noise. This is a very generalized version. If we saw the adversarial example, we could see that FGSM noise are kind of added noise as surround the image. JSM just added the edges. CW just reduced some of the areas and diffused very significant noise in some of the area. So this has a different types of noise and manipulation style of different adversarial attack. This noise can be removed by using different types of different type of image processing filters. This adversarial noise can also be automatically removed by simple environmental factors such as resize. If we resize an image and then size it back, those effect of noises has been removed. or if we rotate, those noise does not have the same effect as before. And if we create a motion like blurring the image has the same type of effect, or brighten the image, which is illumination, that could create the same type of effect. So we did an experiment where different adversarial attacks has been resized, rotated, and motion created by blur effect and illumination created by brightness effect, and we see what is the effect that adversarial image stop as working as adversarial image. We can see that if we resize it 2x and then size it back, adversarial patch attack doesn't work anymore, but FGSM attack works by 20% rate, BIM attack works 28% rate, diffull work as a 90% rate. And if we use to measure the noise and try to detect that using Fourier census transform, mobility transform, and Gabor transform, we can see that FGSM, BIM, and JSM attack has a better chance of getting caught by those transformation techniques. So the destruction rate by the environmental effect or other effect, or detection rate by simple image processing filters, has been correlated over the different attack type. It was the observation of our experiment. We can see the patch attack are very easy to detect but very hard to destroy, and diffull attacks are very easy to detect but very hard to detect and very easy to destroy by simple environmental factor. This is why we suggest to use a minimum noise that could keep the adversarial attack better in the practical field, while the environmental factor does not destroy this as much. We came up with this equation where the noise value is by the 0.5 by 2 to the power n minus 1. N is the bit number of an image. So we can see if the images has the better noise than this, there's a better survival rate in the environmental factor. Based on our observation, we came up with the defense module, while the detector module will detect using filters such as fast Fourier transform or Euler transform. This can easily detect the FGSM, BIM, and other attack. And another module which destruction, which will use the environmental factors such as resizing, illumination, other factors to destroy advanced attacks such as CW and diffull attack. Our destruction algorithm, we use adaptive smoothing, bilateral smoothing, resize. For detection algorithm, we use distance transform, census transform, Fourier transform, and our indicator was signal to noise ratio, histogram, Euclidean distance loss function. Here we provided our result against different uh, defense methods. Our method works as a 99% accuracy for FGSM, which is 99% accuracy against JSM. We also provided our defense against CW attack. Our defense measure outperform other technique on average, and it is sustainable and better defense technique in terms of other facilities, which we will just going to describe in next. Current defense techniques has some limitations, such as they are focused on testing with multiple datasets, but less focus on testing methods practicability. Such as example, they wanted to test with more dataset like ImageNet, CFAI, Open Images, and other different dataset. But when they are testing the testing methods, like they uses the images in a vector format, which is not as machine learning model used in the real life. So those testing has a problem to convert their simulated result in the practical world. And those defense benchmark are most focused on the accuracy and precision, but they ignore the computational cost and feasibility. Like some of the defense technique propose to change the architecture of the ML model, but which is not possible in practical world. Right? We study We study some use cases and we find out that our defense need to work against diverse set of attack type, and it should not reduce the accuracy of machine learning model, and defense should not take large computation time. Defense should not modify learning model architecture. Defense should not need to know all the attacks. Defense should work if learning model changes. Defense should work in cross domain. Defense should not require any information on learning models. Defense should not require a complete training dataset. These are the requirement and feasibility for a defense technique to work on a machine learning model. Proposed a benchmark score, or if a defense technique tested with multiple datasets, it will weight at 10. It tested against black box, white box, target, non-target based and non-target based attacks, it will weight at 5. If a low computational overhead cost, it will weight at 5. It is cross-model and multi-domain applicability, it will weight at 5. If it tested against adaptive attack, it will weight at 10. If no machine learning involved in the defense technique, it will weight at 5. If randomness exists to answer obscurity, it will weight at 10. If no training data needed, it will weight at 10. If no knowledge of learning model needed to know, it will weight at 10. If no modification of the learning model needed, it will weight at 10. If no accuracy drop of learning model needed, it will weight at 10. If no adversarial knowledge needed to generate defense, it will weight at 10. We benchmark some other defense techniques using this, and we find out there is a lot to improve in the existing defense techniques. In summary, our paper proposed a threshold-based solution for adversarial noise detection issues, which has been a big problem for advanced adversarial attack types. Based on this issue, we proposed a two-module defense techniques, while the detector module detect and detection module destroy the adversarial noises. We proposed a more practical benchmark system, which also work on the reliability and feasibility of a defense system.